Alright, we've looked at gravitation between any two masses. So we use Newton's universal law of gravitation. And we got G m1 m2 over r squared. So force between any two masses like that. We've also done some circular motion stuff where anything going in a circle, we were aware that there's a force that's needed for that centrifugal acceleration to cause it to change direction and change velocity, and so we've been using that one. So we want to now sort of look at these situations where there's both of these being used at the same time. So we're going to look at satellites going around a planet like the Earth, because the gravitational force is actually providing the force to keep this going in a circular motion. So it's a gravitational force that supplies the centrifugal acceleration to keep it going in a circle. So looking at that then, you can combine these two ideas here, because the gravitational force here is providing the force for the centrifugal acceleration. So you've got a formula there based on the mass of the planet there, so we do that as a big M there, times by the mass of the satellite over the distance between the two of them, which is from the centre to centre, like that, and that's going to give you the centrifugal acceleration here, or the centrifugal force. So we're going to cheat here and substitute in there. So we're going to cheat here and put in there mv squared over r, having substituted the MAC as mv squared over r. Okay, so looking at that then, you should be able to see that the mass of the satellite here, which is the object that's going around the circle, actually doesn't matter at all. Okay, you can't cancel that out. The radius here will also cancel that one. So you end up with a formula for the velocity of that satellite to keep it going around the planet, in this case the Earth. So that's the velocity there. So it only depends on two things: the mass of the actual planet that it's going around and how far away you decide to place it. So that'll tell you the orbital velocity to keep this in a stable orbit at the same radius. So that's pretty important there. But it only depends on the mass of the planet and the radius that you go to. What this also indicates is if you're going around a planet that was larger at the same distance here, you would find that you need to go faster. So if you had a bigger M, you will find you need a higher speed. And you can look at that as there's more gravitational pull on it if it's got a larger mass of the planet, so therefore you need to go at a higher speed to maintain that same orbit because of the greater pull. Otherwise you'll be pulled down towards the planet. Similarly, if you go to a greater radius here, something different is going to happen. At a greater radius out here, you actually have less gravitational force pulling on you. Your orbital speed can be lower to still maintain that stable orbit. So they're the two things to consider. So that's fairly useful because it'll tell you what speed to begin launching a satellite around the Earth to have it at a particular altitude. So we'll come back to that later. So if we do have a satellite going around a planet there, we've got two formulas we can use. We can use this one here that'll tell us the orbital speed, and that's an easy enough one to work with. So let's do an example of that. So as an example, let's say we want to find out what's the orbital speed for a satellite that's say 1,000 kilometres above the Earth's surface. Now if you're doing that there, we're going to use this formula here. So velocity is equal to the square root of 6.67 by 10 to the minus 11 for gravity. Mass of the Earth, you can look that up, I think it's 5.98 by 10 to the 24 on the formula sheet. And you've got to square root the whole thing, and now at the bottom here, this is where people get it wrong, that radius there has to be the radius of the Earth plus the actual altitude there. Okay? The height above the Earth's surface. So the radius of the Earth, if you look that up, is about 6.4 by 10 to the 6. May actually be the more significant figures than that. Plus, now if you've got 1,000 kilometres, you must change that to 1,000 times by 1,000 to get it into metres. In other words, if you check it, it's 1.0 by 10 to the 6. So just get that into metres, and well, there will give you the calculation. And you get about 7,340 metres per second. So that's the speed you'll need for orbital velocity. Okay? So having done that, of course, you could work out the period then based on that. If you've actually got that, you can then go and work out the period that that satellite will have going around the Earth. So we can actually use this one here now, 2 pi over t, for anything going in a circle, and rearrange that to find the period. So for the period there, you would rearrange this to t equals 2 pi r over v. Some would substitute first and then rearrange it, but I'm going to do it this way. So 2 times pi, and again that radius must be the one including the altitude, so it's 7.4 by 10 to the 6 in metres when you add them together. And the period is going to be there, so velocity we've got at 7,340. So based on that you'll get so many seconds. So it's about 6,300 seconds, around there. So approximately 105 minutes. Now, the other thing to be aware of is there's a very strong link between period and radius for the orbit. So depending on the satellite you want to put up, if you want to put it up with a longer period, you need to actually look at the relationship between period and how high above the Earth it is, or the total radius to the centre there. So when you look at it, you've got two formulas here for velocity. That one there, and this one. One of the questions you could be asked is what radius should you actually place a satellite at to have a period of, say, 90 minutes exactly? So we're trying to have a period of 90 minutes, and we'd like to know, well, how high should we place that? How high do we need to get the satellite up to? Now, if you look at these two individual equations, you can't really answer that question with either of these, because if you try to do this one, we've actually not got the velocity, and we haven't got the radius, so we can't use that to work out a speed and then go and get a period. Over here either, we can't really work out the same thing, because we've got a period there, we've got the radius, no, we haven't got the velocity. So again, we haven't got V and we haven't got R. So just knowing the period doesn't help tell us either of those things. But if you were to equate these two equations and put them together, the fact that root gm over r is going to be equal to 2 pi r over t, because they're both equal to v, you can square both sides first of all, so gm over r, getting rid of the square root, this would be 4 pi squared r squared over t squared. You've got that there. And you can see that there should be some sort of ratio between period and radius here. So if we rearrange this a bit, and maybe we'll get the r on its own here, the r up here will become an r cubed. So that gm there is going to stay where it is, but we're going to leave the 4 pi squared here, so that'll come down to the bottom. And we want to move the t squared up as well, so the t squared will come up here, and you end up with that. R cubed, t squared on the top, so that's it. So you can see there's a proportionality here between t squared and r cubed for a fixed planet there. So it actually turns out that that's a relationship there. Now what this means is if you want a satellite up there with a longer period, you need to place it further away. But it also allows us from this formula here to actually calculate exactly how far that radius should have been. Because if you come and do that here, we could have gone r was this cube root of gmt squared over 4 pi squared. And that would have told you how high you need to place your satellite. Don't forget period needs to be in seconds.